Okay, good morning, everybody. Welcome to the Climate and Energy College. My name's Sonia and I'll be the host for this morning. First up, I'd like to pay our respects to the traditional owners of the land, the Wurundjeri people, and pay my respects to the elders past, present and emerging. This morning, we have Andrew King from Earth Sciences coming to talk to us. So Andrew is a lecturer in climate science in the School of Earth Sciences and an ARC DECRA fellow. He completed his PhD at University of New South Wales in 2015, and before that was at the University of Reading. So this morning he's going to be talking to us about understanding future climates using model time slicing.
I think I've got everything set up. Good. Yeah, thanks, Sonia, for the introduction. And thanks for coming along to hear me speak. Feel free to interrupt me at any point if anything doesn't make sense, by the way. So today I thought I'd talk about climate projections and different methods for making climate projections, and specifically talking about one method which is called model time slicing, and compare it with other approaches. Okay, so I'm going to talk about some of the different methods used just quite briefly before comparing different methods for projections in terms of their uncertainties, what that means for actually how we make and interpret climate projections. I'll then utilize this method that I'm going to be talking about, this time slicing approach, which basically allows us to make different global warming worlds, like 1.5 and 2 degrees, to then talk about nonlinear change, whether we should expect accelerated local changes under global warming, and also to compare transient and equilibrium climates as well. Okay, so there's lots of different methods for making climate projections. The one that most people are probably most aware of is the kind of scenario approach, where we look out over, say, the next 100 years or so, and we have different scenarios, like, I'll try and learn how to use this. So we've got a high emission scenario, like the RCP 8.5, that's called, and we have lower emission scenarios like RCP 2.6. So where we're forcing the climate, we're forcing climate models under different greenhouse gas emission scenarios to make different warmer worlds over time. So that's one approach. You can make kind of a time series based on that kind of approach, which makes it quite attractive. So people can say, if we follow an emission scenario at 2050 or at 2080, we're likely to have global temperatures in this range. Another method, let's see if this works, so is called pattern scaling. This was a method that was implemented to a very high degree in the recent special reports on 1.5 degrees. And it's basically using the fact that climate change has a very distinct pattern. We have more warming over the Arctic than in the tropics, and more warming over land than oceans under transient warming. So as the world warms up, this is the kind of pattern we've observed, and it's the kind of pattern that the models reproduce fairly well. So what a lot of people have advocated for is, if we use our models to look at, say, 2 degrees of global warming, and we see this pattern, we can probably just scale that down to 1.5 degrees, just multiply it by 3/4, and that's a good estimate for a 1.5 degree world. So as I say, that was very heavily utilized in the recent special reports on 1.5 degrees. And then there are other methods like time slicing. So this is where we try and prescribe specific global warming levels. So we take these scenarios that are produced under with these global climate models in CMIP5, for example, and we pick out periods which fit into different global warming levels, like 1.5 degrees or 2 degrees. This is just an example for Access 1.3, one of the Australian climate models. under these two emission scenarios and the years that are pulled out to make a 1.5 and a 2 degree climate. So there's lots of pros and cons of using these different methods. There's a very nice paper by Rachel James, who was a postdoc at Oxford, who wrote a very good summary on these different methods. So I'm going to be comparing a couple of these different methods. I'm mainly going to be comparing these two methods, and I'm going to be talking about the validity of the pattern scaling method. So as I say, there were pros and cons to each. And in the past, I'll just go back a second, this has been by far the most dominant method of making climate projections overall in the past. And it's only really in the recent period when we've had policy making focused around specific global warming levels that other methods have come into the fore more, like this kind of prescribed global warming level projections method. So since the Paris Agreement, this has become more popular. So I'm going to talk about comparing now some of these different projections, comparing the kind of the traditional approach to projections where we look forward in time versus global warming level projections where we're looking at projections as a function of global temperature as opposed to time, really. So I'm basically, well, the point here is that we really need to understand the characteristics of these different ensembles when we're making these projections in order to make appropriate inferences from them and make appropriate projections. So I'm going to talk about comparing these two types of projections. So comparing time periods from the different CMIP5 projections. So say comparing the 2040s with the 2060s or the 2080s, and comparing projections as a function of global temperature, so 1.5 or 2 or 2.5 degrees of global warming. And it's important to note that there's lots of different sources of uncertainty in different climate projections, and they're likely to be of differing importance depending on the type of projection we're interested in. So this is a figure a lot of you might have seen before from a paper by Ed Hawkins, where he's quantifying sources of uncertainty through the 21st century. So basically from an initial condition into the future. And this is for the globe, this is for a location, a local projection. And there's lots of different sources of uncertainty. Near the beginning, we're quite concerned with internal variability, which is represented by the orange segment. A lot of uncertainty in near-term projections based on things like whether we're in an El Nino or a La Nina. And that's more important at the local scale than the global scale. There's scenario uncertainty, which is the green region. So near the start, that's not very important. If we follow different RCPs and the projections start in 2006 and we look at 2010, there's hardly any difference because of scenarios. But by the time we're getting into the late 21st century, scenario difference is very important. And there's also model uncertainty. And that's really composed of a few different uncertainties. So different climate models warm to different levels following the same forcings. So that's related to this concept of climate sensitivity. But there's also another factor in that the models have different patterns of warming into the future slightly. And that's kind of folded into that uncertainty as well, especially on the local level. So we've got these different sources of uncertainty. And if we're thinking about projections forward in time, different uncertainties are more important versus projections for given global warming levels. And I'll talk about that more in a second. Sorry, Malta.
On the last graphs, if you were to normalize the models to current period, then the orange part should be 100% in the beginning, because all the models would be normalized to the current period. So basically, the uncertainty in the next year is only variability, and then it emerges. So it depends how these slices are at the very beginning, depends on what your reference period is.
That's true. And I think for this figure that Ed made, it's a combination of the reference period and there's a smoothing applied as well. So the first year isn't just the first year. But yes, I agree.
The first 10 years are why?
Yeah, the first 5 years or so. I think that's just because the projections start in 2005 and it's a year from 2000, I think. Yeah, I'd have to go back to Ed's paper to remember fully. Yeah, okay. So there's 16, so I'm using 16 climate models, and these CMIT5 models, and I'm basically, constructing these two parallel sets, these two parallel ensembles to compare. So I've got these time period projections, which are on the top there. I inadvertently made something that looks a bit like the warming stripes that Ed actually quite often makes, and you might have seen for observed temperature change. So I'm constructing them for given decades and given scenarios. So for example, the 2050s under RCP 8.5. So in this case, I'm removing the scenario uncertainty deliberately, but there is still uncertainty due to model uncertainty, climate sensitivity differences, pattern differences of warming, and also internal variability. That's contributing to the uncertainty in that ensemble. In this case, the changes were calculated relative to a recent 30-year baseline period and projected forward. The uncertainty, as Marta was kind of alluding to, the uncertainty here would be very, very strongly dependent on the reference period, since the climate models have warmed to different levels up to the present. And I'm comparing these with my global warming level projections. I've just abbreviated that to GWL here. So this is where I take these time slices from the models which correspond to given levels of global warming. And this is within 0.2 of a degree from the target level, so whether it's 1.5 or 2 degrees on decadal average smoothed temperatures. So this is trying to damp the effect of internal variability on the selection of the years that go into these ensembles. And this is with reference to a pre-industrial period equivalent, which is using the models corresponding historical natural simulations. So these are simulations that remove anthropogenic forcings over a century. So different people use different pre-industrial periods. Ed, I should have actually added a reference. Ed Hawkins actually has another paper on that, as does Andrew Schurer. Very nice discussion of the differences caused by representing pre-industrial climate in using different periods. This is quite a suitable way if you're using models because it's very long. Whereas in the IPCC report, for example, using the late 19th century is favored, but it's a shorter period with volcanic eruptions, which have an impact as well. So I've got these two sets of ensembles, and I'm trying to compare them. I'm comparing the spread in these ensembles. I'm trying to do it for comparative global warming levels and periods. So for example, if I'm using only the RCP 4.5 time periods, I'm comparing in the later 21st century, 2.5 degrees of global warming with, say, the 2080s in RCP 4.5. Whereas if I'm using RCP 8.5, I'm comparing with the 3.5 degree warmer world. So it's more like it's related to the warming actually under each scenario. And as I was saying before, the uncertainties in these different, the ensemble spread in these different ensembles is composed of different elements of these uncertainties. So in the time periods, we have uncertainty due to internal variability. We have uncertainty due to, no, not uncertainty due to scenario. I've controlled for that. But I do have model uncertainty related to both climate sensitivity and the pattern of warming. Whereas for the global warming levels, I've controlled for climate sensitivity to an extent by deliberately picking the global temperature to be roughly the same. But I do have uncertainty related to the time instead. So for slow warming processes, there will be more spread in those instead. And that will become clear in the results in the next slides. So this is, you can ask a question now if you want.
Is it global mean surface air temperature or global mean surface temperature?
Global mean surface air temperature. Okay. So I'm comparing, yeah, if you have any questions, just ask at any point. So this is just illustrating that I'm comparing like with like in terms of global average temperature. But I'm really concerned in the spread in the ensemble. So the global average temperature itself doesn't have too much of an impact anyway on that, that quantity. So firstly, how does the spread actually evolve in each ensemble? So if we compare the 2020s in RCP 8.5 with the 2030s in RCP 8.5, this is the ratio of just the 90% range in annual average temperatures in those two ensembles. So where it's yellow to red, it's higher in the 2030s. Where it's blue, it's higher in the 2020s. So you can see in general, the spread is increasing. And actually, if you take it to an extreme and compare the 2090s with the 2020s, the spread has really increased hugely. And that's not particularly surprising. That's basically the model's different climate sensitivities and different patterns of warming. But if we do the same with our different global warming levels, so this is the same quantity, but comparing with the global warming level ensembles, 2 degrees versus 1.5 degrees, and 4 degrees versus 1.5 degrees, the spread also increases quite a lot, which is interesting and possibly not what you'd expect as logically, and it's basically due to more differing points in time being sampled to make these warmer worlds. So where time is also important in terms of the level of local warming, that causes the spread to increase. And this is particularly true in places like the Southern Ocean, where the warming is so slow that it's more time dependent than actual global temperature dependent, which is quite an interesting characteristic. So then if we actually start comparing these ensembles with each other, so this is now comparing the 2020s in RCP 8.5 versus 1.5 degrees, you can see, because it's mostly blue, there's more spread in the 1.5 degree world than the 2020s world. But if we're looking at the 2090s in RCP 8.5 versus a 4 degree world, the spread, it's more red over most of the world. So the spread is much higher in the RCP 8.5 at that time than in the 4 degree world. This is not true in places really where slow warming processes dominate, like the far North Atlantic and the Southern Ocean. So another way of looking at this is actually looking at when that change occurs, when the ratio flips over. So this is just mapping out for the RCP 4.5 versus global warming level projections and the RCP 8.5 time periods versus global warming levels, in which decade that flip occurs in the ratio. And you can see that over most land regions and generally outside the high latitudes, around the mid-21st century, the ratio changes, it goes above 1. So the spread is higher in the time period than in the global warming level projections. So the spread is increasing in both ensembles, but it's increasing at a much higher rate in the time period projections than the global warming level projections. And another way of looking at this is to look at regions of the world, so things like Georgie regions, which are these subcontinental areas where we often look at regional projections. And this is just plotting for the comparable periods So like the 2020s versus 1.5 degrees, 2030s also versus 1.5 degrees. In RCP 4.5, the ratio of the spread and whether it's higher in the time projections or the global warming level projections. And you can see this general trend in all the regions towards highest, the ratio moving above 1. This is only for land surface regions, I should have mentioned. I've just picked out a few which are the highest and lowest by the end of the 21st century under RCP 8.5. So the ratio is higher in particularly dry areas of the world, areas that are drying, like the Mediterranean, possibly related to uncertainties in rainfall projections as well. So for places like the Sahara, there's a lot of uncertainty. So the point of this is really to show that there's lots of uncertainties inherent in climate projections, and they are different dependent on the type of projections you're using. And this needs to be considered when you're making projections. So we know that there's uncertainty increasing in both projections as a function of temperature for the global warming level projections and as a function of time. But it's increasing more as a function of time than as a function of global temperature. So this is important in designing and implementing, especially regional projection analyses. If your spread is increasing and you're interested in extremes, a very basic analysis could mean that you're overestimating changes in hot extremes, for example. So you have to control for this kind of effect. Are there any questions actually at this point? Because I'm going to move on to the next section. Okay, so I'm now going to kind of utilize these global warming level projections a bit more to show some of the benefits of using this kind of climate projection. The first thing I'm going to talk about is nonlinear change. I gave a seminar last year which used some of these results, but there will be some new results in there as well. So hopefully it won't be, most of it should still be somewhat new at least. So this is basically, one way of framing this is the pattern of global warming going to change? Do we expect this pattern that we've seen, the observed warming we've seen to date? This is just taking the NASA GISS temperatures data set over the late 20th century and looking at the trend. And basically we see this pattern, more warming over the Arctic than other regions, more warming over land than oceans in this transient period of warming. So basically, can we use these global warming level projections to look to see if this pattern of warming is different under higher levels of global warming? So another way of looking at this is to plot, as a function of global average temperature anomaly, the local average temperature anomaly, and see if it follows a linear pattern. So is it a straight line, or is there an acceleration as there's more warming locally as a function of global warming, or is there a deceleration? And this is important for us to know. This is testing the validity of the pattern scaling method, which was really heavily utilized in that 1.5 degree special report from the IPCC. Is this actually a reasonable approach to be using? So there's different ways we can look at nonlinear change. There's lots of different methods we could try and estimate or quantify the nonlinearity. So I've used two different methods that I'm going to compare very briefly. One of them is just taking for each half a degree increment of global warming, so 2 degrees, 2.5, 3 degrees, is the warming, how much is that line actually different from the linear extension from the pre-industrial period? So is at 2 degrees, is it just actually 4/3 of 1.5 degrees, or is it different from that? How different is it from that? And so forth. So you can do this for multiple levels of global warming, and you can add them together as well. So I've called this the sum of departures method. But another method is just to do a power fit. So just to see if you fit with a curve, is the power b greater than or less than 1? So I did this as well. And this is basically what I find. So this is for boreal summer on the top. So I should say, is it austral winter on the top, austral summer on the bottom. On the left is the sum of departures method. And on the right is the power fit method. And this is actually just looking at model agreement. So this is taking each of these CMIP5 climate models and whether they agree on the sign of the nonlinearity. So if it's orange to red, they're in general agreement that it's an acceleration locally. If it's blue, they're in a general agreement there's a deceleration locally. And the first thing you note, see if this works, is that these patterns, I mean, this general pattern we see based on the one method is reproduced with the other method. They're in very strong agreement. So it's fairly robust. How you define the nonlinearity or how you quantify it doesn't make a huge difference to the results, which is nice. And the other thing you'll note is that there are general patterns here. So over northern hemisphere land regions, particularly in their summertime, there is likely to be an acceleration in local warming. So that obviously is quite important for them to know. Whereas for ocean regions, especially slightly more in the winter hemisphere, but in general over ocean regions, there's a slight deceleration in warming projected as we move to higher global temperatures. So this is important implications, because if you're comparing regional projections based on, say, global warming levels versus a pattern scaling approach, you would get slightly different results if there's big areas of red or blue here. So if there's areas, for the areas in red here, if you use a pattern scaling approach, depending on exactly how you implement it, you might underestimate the projections for warming slightly. So there's lots of different ways we can utilize this type of, these results. So looking at the nonlinear change, and we really want to understand why the models produce nonlinear change and the processes behind that as well. So what's causing the different models to produce different warming patterns? And one way we can do this is looking at the local level. We've got our different CMIP5 climate models. How much we can quantify the nonlinearity in each of the CMIP5 models, but we can also quantify the things like the change in precipitation, for example, as we move to warmer worlds. So if you were looking at a particular location and it was following the blue line on this kind of schematic, that would mean that the models which have accelerated local warming tend to have increases in precipitation and vice versa. Whereas if they were following the brown line, the models with accelerated global warming up here would have reductions in precipitation and vice versa. So we can look at this at the local level to try and diagnose why the models are responding in different ways, why some models produce accelerated warming or decelerated warming. So if we look firstly at austral winter, what we see is, so these brown and blue grid boxes are designed to try and match this. So where it's brown, you're getting this effect where the models with accelerated local warming have decreases in precipitation. And basically what we're seeing in the northern hemisphere mid-latitude regions is that the models, and this is where most of the models actually have accelerated warming, the models with the strongest accelerated local warming have reduced precipitation and vice versa. This is also true if we look at austral summer and we look at northern Australia, we see this effect. So the models with accelerated warming are seeing big reductions in precipitation and vice versa. Over most ocean regions, it's mostly blue. So the models with accelerated warming have increases in precipitation. So what we're seeing over land is that the models that dry out are producing accelerated warming, and this is related as well to the composition of heat fluxes. So there's this general shift because there's this drying effect. There's a reduction in the latent heat flux relative to sensible heat flux. So that can exacerbate warming. So there's lots of studies that have shown this for given heat waves in places like Central Europe. They're often preceded by drier conditions, and there's a change in the heat flux composition that exacerbates warming. What we're showing here instead is that under climate change, and this is partly explaining changes in the pattern of warming, and not just for given events, like given heat waves that have been shown before. Over most ocean regions, especially where there isn't really a strong dynamical shift, so where it's mostly just a thermodynamical change that's going on as the world warms up, what's happening is that models that warm faster tend to get wetter. And this is partly because over the oceans there's an abundant supply of moisture. Many of you have probably heard of the Clausius-Clapeyron relationship. So the fact that when the temperature rises, the air can hold more moisture. And what we're seeing over the ocean is, as the models which have accelerated warming in a particular location can hold more moisture and precipitate out more efficiently, relative for that same location to the models that don't have that accelerated warming. So what this is showing is that this kind of analysis is only really possible by using specified global warming levels. If you're using traditional projections where you're looking in time at the change in temperature, it's very hard because the global temperature isn't constrained. You can't look at the local level at the differences between the models. So there's this loose constraint applied here that allows us to look at the local differences and explain them, which is useful. So we can look in a bit more detail at specific regions, and one I've looked at is Northeast Australia. So this is a region where we had this very strong relationship where the models that were drying out had accelerated warming. So this is looking at austral summer, and what I'm doing here is, I should really be using this, sorry. The models with accelerated warming in this region, I'm correlating with the change in temperature everywhere across kind of this region here. And I'm doing the same for the change in precipitation, the change in mean sea level pressure going to higher levels of global warming, the change in incoming shortwave radiation at the surface, and the change in the evaporative fraction. And what I'm showing here is that models with accelerated warming over Queensland in summertime tend to have warming over the Central Pacific, drying locally but increased precipitation in the Central Pacific, a decreased mean sea level pressure in the Central Pacific, and also increased sunshine intensity and decreased evaporative fraction, which means a greater role of sensible heat flux relative to latent heat flux. So essentially, one other way of putting this is that models with accelerated warming seem to have a tendency for a more Central Pacific El Nino-like warming pattern. And yes?
So fascinating stuff. Just one step back to understand. What's the exact term? And sorry that I missed that. Models with accelerated warming. Are you there comparing patterns of models or yeah, those, I mean, could it also be, could one single model where you look at a lower temperature level and then later in time at a higher temperature level under an RCP 8.5 scenario, that would also fall into this analysis? Or do you only compare models at the same time that have either higher or lower warming?
So it's taking, what I'm doing here is I'm taking what's going on in Northeast Australia in summertime and taking the models by their nonlinear temperature change, and then comparing at each location around in these regions, correlating with the change in each variable from 1.5 to 3.5 degrees of global warming. So it's the change in temperature at every location correlated with the nonlinear change in temperature in Queensland, in the case of the top left plot. And then that's done equivalently for all the other variables. So it's change in MSLP at each grid box correlated with nonlinear change in Queensland temperatures. So what this is showing is that the models with accelerated warming in Queensland in summertime tend to be negatively correlated with MSLP in the Central Pacific. So the models with accelerated warming tend to have more of a reduction in MSLP and vice versa. Does that make sense?
The determination whether a model has accelerated warming in Northeast Queensland is taken by a comparison across different scenarios?
Across different models.
Across different model for one scenario?
This is across, well, it's across global warming levels. So it's not really a function of scenario. It's just
so it can be
level.
both. It can be, the accelerated warming can also play out over time in one single model. Anyway, we can discuss it.
Well, this is trying to take time out of the equation.
So Andrew, maybe just to think about it another way, if you looked at RCP 8.5 and you looked at the spread between those models with high warming and those models with low warming, you should get to something similar to this?
Not necessarily. Not necessarily. This is saying for the change, this is because it's controlling for global temperature change. So going from a 1.5 degree world to a 3.5 degree world in each model, it's comparing locally that change in, say, MSLP between 1.5 and 3.5 degrees with the non-linearity in that model from 1.5 to 3.5 degrees. Specifically the non-linearity in Queensland summer temperatures here. So the models with accelerated warming as a function of global temperature, so forget about time, just as a function of global temperature, the models with accelerated warming in Queensland tend to have a reduction in mean sea level pressure in the Central Pacific. Okay, so I think because I'm looking at projections in a different way from the normal way, I probably need to be a bit slower in how I explain them. But yes, essentially, the models with accelerated warming over Queensland as a function, accelerated local warming as a function of global warming, tend to have a more Central Pacific El Nino-like pattern. And I've just pointed here to Mandy's recent paper that many of you will be aware of, Mandy Freund's recent work that shows that over the historical period, there's been an increase in Central Pacific El Niños relative to East Pacific El Niños. And she doesn't attribute it to human-caused climate change. But if that trend were to continue, that Mandy's work has found for the past, then we might be more likely to expect an acceleration in summer warming in Queensland as a function of global warming. Okay, so the result of this, so the point here is that in moisture-limited regions, so places like Northeast Australia, but also Central Europe and the Western US, for example, there's this really strong difference between models, a strong inverse relationship, where some models are warming but getting wetter, and there's some models that are locally warming much quicker as a function of global temperature and getting drier. So there's very strong, this partly explains the difference in climate projections between models for these regions. So this has the effect of, you can construct alternate climate projections based on whether we're getting wetter or drier because of the nonlinear change in these particular locations. So for example, if we're looking, so this is as a function of global warming level, looking at the probability of having a hot summer in Queensland that exceeds the observed record. And the blue bars are for the half of the CMIT5 models that are getting wetter in that region. It's roughly half. and the brown bar is for the half of the models that are getting drier. And you can see that there's difference in projections, and basically there's faster warming as a function of global temperature if we follow the drying pattern in this region. And the difference is more than the difference between half a degree of global warming increments, the difference between the dry and the wet models. So we've just had this whole IPCC special report on the difference between half a degree increments in global temperature. But on a local scale, or even quite large regional scale, the difference in projections, the uncertainty in the change in rainfall, is coupled to the uncertainty in the pattern of warming that results in actually a bigger difference in projections, a bigger uncertainty in projections than the difference between 2.5 and 3 degrees, or 2 and 2.5 degrees of global warming. So this is a really important point, that there's this huge uncertainty in regional projections. It's partly explained by the nonlinear change locally in warming. It's partly explained by the change in the pattern of warming. So just to conclude this point, this section of the talk, what I'm showing is that there's different relationships between, well, firstly, we can quantify nonlinear change in the models locally, and we can relate that to precipitation change. And we can kind of explain why some models have accelerated warming and decelerated warming locally by looking at these other changes in these other variables like precipitation, mean sea level pressure, etc. And this is showing that the nonlinear change in the models is contributing a lot to the uncertainty in regional climate projections. And it's something that we're going to need to try and constrain to have more confident regional climate projections. And the main point I'm trying to make is that this kind of analysis is only really possible by using this kind of method of climate projections, this global warming level projections. If you're looking at traditional projections as a function of time, there are so many other things going on. There's the different climate sensitivities of the models. You can't really do this kind of analysis, and you can't constrain the global temperature to try and understand the differences in local temperatures so easily. This work was recently published in ERL. So finally, I'm just going to talk about another way we can use this type of method to understand future climates. And this is about comparing transient and equilibrium climates. So at the moment, we've got, we're rapidly changing the composition of our atmosphere by emitting greenhouse gases. And we've got transient climate change, whereby we're warming the climate very quickly. But the Paris Agreement is aiming for stabilized global temperatures, preferably at below 1.5 degrees above pre-industrial levels. So it's quite important that we try and understand the differences between transient and equilibrium climates. So what I'm going to try and demonstrate here is that using this type of method, we can try and quantify the differences between transient and near equilibrium climates. They're not in full equilibrium, it's worth pointing out, but they're close to equilibrium. So I'm using here the projections that you're kind of used to over the 21st century, the RCPs. This is very much transient warming, where the global temperature is rising quite quickly. And I'm also using these extended RCPs, which the global temperature stabilizes to a degree over the following 2 centuries. So I'm comparing the 23rd century in these extended RCPs, that some climate modeling groups ran for the last IPCC report, and comparing those with transient warming over the 21st century. And the way I'm doing this is I'm taking, so that all the models warm to different levels. They have different equilibrium climate sensitivities. So this is just looking at the 4.5 scenario and showing that some climate models warm by as little as about 2.5 degrees above pre-industrial levels, whereas some warm by over 4 degrees. So there's this big range. But what I can show is that if you take for a given model, the warming in the 23rd century, you can compare that with the equivalent model's transient warming using RCP 8.5 over the 21st century, and find the point in time here where the global average temperature is roughly the same as it is in the equilibrium scenario. So it's again constructing two ensembles, a transient ensemble constructed from RCP 8.5 and an equilibrium scenario constructed from the 23rd century of these runs. So they're taking different points in time, depending on the model, and different levels of global warming. I can show, I haven't got the figures here, but I can, I could circulate them if there's interest. I can show that the level of global warming isn't important in quantifying the difference between the transient and equilibrium climates, which allows me to subtract the global warming level and make these two ensembles, the transient and the equilibrium ensemble, and just in anomaly space. So I'm able to have these two ensembles and compare them directly. Yeah. So, were you going to ask something, Walter? You were sorry.
That statement that you can show it irrespective of the temperature level, does that have to be limited to the extent that if you look at very low levels, then your transient time slices move closer to current levels where you have different forcings at play. So if you move to 1.5 degrees, or then you are closer in time in RCP 8.5 to higher aerosol emissions. Therefore, you would see a East Chinese cooling blob compared to the long equilibrium, which is attributed to the forcings, not to the transient versus equilibrium.
That's a really good question. So I was only comparing, so I did some sensitivity tests just using the models, comparing the models by their global average temperature. So comparing the land ocean temperature difference and the local temperature change with the difference between the transient and equilibrium worlds. So I could send you some figures. It's probably easier, but I don't think I ever, because I'm only, the gray bars here show what I'm sampling from the transient world, and I think I'm just not close enough to the start of the 21st century. But it's a good point that the point I just made about them being not dependent on global temperature is only probably applicable to a point. It's probably not applicable here. So I shouldn't make as sweeping a statement as I did. That's true. But certainly within the analysis we were doing, it wasn't an important factor. So this is just showing actually the different models, and there's multiple simulations for some models. The levels on the right, just the level of warming that we're looking at, the level of global warming in the ECP, and then the equivalent period we're taking from the transient world. So this is in time. So we're taking mostly periods from the 2050s and 2060s rather than say the 2020s, where the aerosol effect would be really important. And you can see, I've got about 12 or 13 climate models that I'm using here that have all the data that I need to do this. So then we could start looking at the difference between the transient and quasi-equilibrium warmer worlds. And this is just showing for June, July, August on the left, December, January, February on the right, the difference between a transient and a equivalent quasi-equilibrium climate. So so what we're showing is that in a transient climate, the same controlling for global temperature, we've got more warm temperatures over the land masses and over the northern hemisphere in summer, again, relative to the near equilibrium equivalent. The stippling shows agreement. At least 3/4 of the models agree in the sign of the difference between the transient and quasi-equilibrium climates. So you can see, again, where slow warming processes dominate, the more local warming in the Southern Ocean, for example, in the equilibrium climate relative to the transient climate. So what this means is, if we were to follow, sorry, okay, I'll try and speed up a bit. If we were to follow a 1.5 degree scenario where we had an overshoot and then stabilization, we would expect that the Southern Ocean would be much warmer in that stabilized version of 1.5 degrees than the transient one, where we just go through it quickly. But the opposite would be true over land regions. So this is a big benefit for where most people live in terms of the temperatures they would experience. In a stabilized climate, they would tend to experience cooler temperatures than in the transient equivalent climate. And this is just what this shows in terms of looking at the population experiencing different differences in between transient and quasi-equilibrium climates. I'll just speed up a little bit. But this is what these plots are showing, is that the difference between transient and quasi-equilibrium climates is actually really quite significant. And this is comparing it as a function of the difference between the Paris Agreement targets. And where it's red, the difference between transient and quasi-equilibrium climates is greater than the difference between 1.5 and 2 degrees of global warming. So this is, again, especially true in the slow warming regions. But even over many land regions, it's quite a significant fraction of the difference between the Paris Agreement targets. We're talking on average across the whole globe about 40% of the difference for an average location on the world's surface. So this is important because it's kind of implicit in the Paris Agreement that we're talking about an equilibrium climate, not a transient climate. But it makes a huge difference if we're thinking of a transient warmer world at 1.5 degrees or at 2 degrees versus a stabilized climate at 1.5 or 2 degrees. The difference is very big. It's bigger, actually, in some places, and even where it's not in the red area, it's still quite a big fraction of the difference. So this is a really important thing to consider when making projections for future climates at the Paris Agreement global warming levels. You will get different answers if you're looking at transient or equilibrium climates. I'm going to skip over this, I think, in the interests of time a bit. And just go to the end. Sorry, Sonia. So what I'm showing here is that there are large differences between transient and quasi-equilibrium climates. And that really, when we're looking at projections of future climates, for example, at the Paris Agreement global warming levels, we need to be really clear in the framing of our experiment, whether we're looking at a transient warmer world or an equilibrium warmer world, because whilst most policy making is made looking at short time periods, it's important that we acknowledge and communicate the difference between climate projections between transient and equilibrium climates with respect to the Paris Agreement warming levels, because we'll get different amounts of local warming and different projections for extremes, especially heat extremes, if we're looking at a transient 1.5 degree world versus an equilibrium 1.5 degree world. So this has important consequences. Under an overshoot and then a stabilization scenario, you can get very big differences between what the local climate will look like, even if it's the same level of global warming. And those differences are actually bigger in poorer regions of the world. So it's even harder it's even more important for those regions that we're communicating clearly the difference, the framing of our experimental designs when we're making climate projections. Okay, so I'm just gonna, this is my final slide. So in conclusion, hopefully I'm showing that for climate projections, there are differences in their characteristics that are really important to consider when actually using them. And projections based on global warming levels do offer some benefits relative to traditional climate projections, which are based on time and scenario. We can actually conduct some analyses that we couldn't really conduct under the traditional methods, which I think is potentially really useful. One thing I've showed today is that the pattern of global warming is likely to change a bit in the future as a function of global temperature, and that uncertainty in that change is tied to changes in things like precipitation, and that transient and equilibrium climates are substantially different from each other, which isn't too surprising a result, but it's really important that we explain this when we're framing climate projections. Thanks.
Okay, I think we have time for 2, maybe 3 questions. Yes? All right, let's have the online question first. Yep.
Hi, Michael. We've got Michael Gross from CSIRO. I'm going to pass over to you, Michael. Go for it. Are you there, Michael? Can you ask your question?
Hello, can you hear me now? Hello.
Hi, Michael.
Hi. So I've got actually 3 questions, but maybe I'll just ask the most important one. So thanks very much for that. That's fantastic. And as you probably know, we're working on applying new techniques to regional climate projections for Australia and then also out into the Pacific. We're really considering all these different, what I think are being called dimensions of integration by the IPCC, whether you frame it in terms of RCPs, levels of global warming, cumulative carbon emissions, etc. And we could choose one, or we could actually think perhaps a hybrid approach might be useful, where to report on the Paris Agreement targets, we use the techniques you've mentioned because they're so policy relevant to 1.5, 2 degrees levels of global warming, but then report on the higher RCPs as they are. And this kind of scheme kind of might have the most utility to the most people. And it seems to be justified from your results. The lower targets of global warming are more appropriate to examine that way. But it would also depend on user feedbacks, whether people would be happy with this kind of hybrid approach of reporting on the higher ICPs and the global warming targets for the Paris Agreement. And so I was just kind of interested in your feedback there.
Yeah, so basically I think I agree with you, Michael, that a hybrid approach is probably best. I kind of was using this talk to try and sell the idea of global warming level projections a bit more, partly because historically we've been more focused on the RCP type projections approach, but I agree a hybrid approach is probably best. The general feedback I've had is that whilst the global warming level projections are more policy relevant, some people like to have time series, basically, and they like to see how things change or might change over the 21st century. And I think possibly offering both might be the best solution.
Okay, we've got time for one more. Zebedee, you have a question, and we'll make it a quick one.
Thanks. Yeah, following on from that one, on the one hand, you've shown that global warming level analysis is very useful and allows you to make a whole bunch of conclusions you couldn't otherwise make. On the other hand, you've shown that transient and equilibrium climates are very different, and you need to make that difference clear. Is there a contradiction there because global warming level projections necessarily pick out different points in time?
So I mean, they are, so the projections for global warming levels, taking levels during the RCPs are transient, and it's important that we frame them in that respect. But I don't think it's a contradiction as long as the framing is clear. So as long as we are clear in what climate projections we're using and how we're forming them, I think both are useful. People are interested in transient projections and in equilibrium projections, but they are different. So I think it's important just to acknowledge that difference and just be really clear on it.
Okay, we'll wrap up there, but do you have time afterwards if there are more questions? Yeah, so if you have more questions, come and speak to Andrew, but if you all join me in thanking him one more time. And I almost forgot, we have a couple of upcoming seminars. We have Paul Burke on Wednesday the 22nd, explaining spatial variation in small-scale solar uptake across Australia, and Jane Hyder on the 29th of May, aggregation in renewable energy themes and challenges. Thank you.